Well, good morning. Last class was zircon and zirconia, and this class is fused cast refractories, and they're in a group of refractories that are usually called special refractories, um, because of their limited production quantity and their high cost. They're usually called special. But for the fused cast refractories, there's four types I'm going to go over, the most common ones. Alumina zirconia silica is an AZS refractory, alpha alumina, and then beta alumina, alumina chrome, and MgO chrome. Um, those are the four types that I'll go over today. And we'll follow the same pattern we've been following. We'll look at the raw materials, the phase diagrams, how these are made, what their microstructure looks like, and a few of the key, most important properties. So AZS, Al2O3, ZrO2, SiO2 is primarily used in glass tanks. These materials have excellent corrosion resistance, especially due to the zirconia content and the low porosity. So these are about 50 to 65% alumina, 10 to 40% ZrO2, and the balance SiO2, 10 to 20%. So these are cast into large blocks and line glass tanks. Al2O3, there's alpha alumina, and we also mentioned beta alumina, which has the sodium present. So alpha alumina is approaching 100% alumina, and then beta alumina is roughly 94% alumina and about 6% sodium. These also line glass tanks because the alumina has good corrosion resistance, but they're also used as abrasives. So the cast blocks are crushed and they can be used as abrasives because they're very hard materials. Then the alumina chrome, that's used to line fiberglass tanks. Alumina is about 70, 80%, and then the chrome is the balance 20 to 30%. So the fiberglass tanks can be lined with the alumina chrome material. As these materials go through the corrosion process, they contaminate the glass, and the chrome, Cr2O3, colors the glass. A small concentration of chrome oxide tints the glass pink. Obviously, a large concentration would make it purple. So when you're making fiberglass, you don't care if the color's off a little bit. So they're excellent in terms of corrosion resistance because of the high chrome content, but they can contaminate the color of the glass. So they're used in applications where the color isn't important, like for making fiberglass. And then the MgO Cr2O3 refractories are used in steel plant refractories. Maybe in electric arc furnaces and high wear areas. MgO content, maybe 59%, Cr2O3, 19%, and then you have alumina, silica, and the iron oxide, 6, 3, and 13%. So a typical MgO Cr2O3 refractory that's been enriched with MgO. So the raw materials for these, we've really discussed all of these. You're usually using a high purity version of any one of these raw materials. Silica, the alumina silica materials, there was a range of different alumina silica refractories based on alumina content, high alumina, magnesia, the chrome ore, zircon, and zirconia. So high purity versions of these raw materials make up the fused cast materials. So this is the ternary phase diagram for alumina, zirconia, silica. Here's 100% alumina, 100% zirconia, and 100% silica. So this side of the phase diagram, zirconia to silica is basically the binary for silica zirconia, and zircon is the only compound, and that's right here, ZrSiO4. The binary for zirconia and alumina, there are no compounds here. And then the binary for alumina silica, we have mullite, which we discussed. So there's one compound here, 3Al2O3, 2SiO2, that's mullite. So there's the corundum phase field, alumina. There's the mullite phase field, 3Al2O3, 2SiO2. Badylite phase field is here, that's ZrO2. This is zircon phase field, ZrSiO4, and then over here would be silica SiO2. The dotted lines on these phase diagrams are just estimates. So this portion of the phase diagram, the lower left-hand corner, has been worked out. The lines are solid. The rest of it on this particular phase diagram is an estimate. But the fused cast refractories are made in this portion of the phase diagram. The arrow indicates a eutectic at 1790 degrees C. That eutectic is 54% alumina, 28% ZrO2, and 18% SiO2. So this small area right here that's crosshatched in this circle here, oval shape, is where the fused cast refractories are made. So the AZS refractories are made very near to this eutectic. So they're going to be a little bit higher melting than 1790 degrees C. So actually in this little oval shape, the melting temperature is slightly above 1800 degrees C. There's a temperature contour right here, 1800, and there's another 1800 right here. This one looks like it's about 1750. So these are pretty high melting point materials. And they're made pretty close to that eutectic. This is the alumina Na2O phase diagram. I showed this one before. This is 100% alumina on the right-hand side. On the left-hand side is NaAlO2. So about 85% and higher alumina, you're in this phase field, alpha alumina and beta alumina, and it melts at 2000 degrees C. So it's a high temperature material. If you're to the left of beta alumina, Na2O11Al2O3, if you're in this area, 1580 is where this material is going to melt. And if you're even lower, looks like about 75% alumina, you're going to be down here 1410 degrees C. So you have to be above 85% alumina in this type of fused cast material. The alumina chrome is a complete solid solution. Alumina on the left-hand side, it has a melting point of about 2045 degrees C, and Cr2O3 on the right-hand side, it melts around 2275 degrees C. So they're high melting point materials. And then you can see the bottom curve here, the solid line is the solidus. Everything below that is solid. So these are also high temperature materials, the complete solid solution. And then the MgO Cr2O3. This is MgO on the left-hand side. It melts around 2800 degrees C. And this is the spinel MgCr2O4. That's 80% and 80% Cr2O3. And that's your spinel composition right there. So there's a little bit of MgO solid solution. There's a spinel solid solution. And then this is the MgO spinel phase field. And if you look at the solidus curve up here, it's over 2300 degrees C. So another high temperature material. So all of the fused cast materials are relatively high temperature. You're starting out with relatively pure raw materials. So you start out with the raw materials, the powders, they're mixed, and then they're melted. So they're melted in an electric arc furnace, and depending on their melting temperatures between 1800 and 2600 degrees C, they're cast into large ingots, and they're utilizing carbon as the primary um, mold material, or even sand molds, maybe for lower temperatures. But the carbon or graphite is very stable at high temperatures. So these ingots, they can be quite large. If you, after cooling, you can grind these materials and form a grain, which can be used for other refractory applications. It's going to be a large crystal size, basically low porosity. Can also be used for abrasion materials. And then if you anneal these shapes to remove the stresses from cooling, you're going to anneal them for 1 to 2 weeks. So it's a very slow process. And then those large shapes that are on the order of feet, very large, they can be machined so that they fit together. So the surfaces are machined. They're basically made flat and parallel. So the way these are melted, you have a metal shell, basically a large crucible. It's water cooled. So you have a metal shell that's water cooled. You put in the powder or whatever composition you're going to melt. Then you lower the graphite electrodes and strike an arc and form a melt in the center of this crucible. And then you have unmelted material that is in contact with the metal shell, and it's water cooled, so there's a large temperature gradient. So this is unmelted powder that's containing the melt. So that's the insulation. It protects the metal shell, and it forms the refractory lining. So it stays as a powder, not molten because of the high temperature gradient. So you're melting the material and basically in its own powder because of the steep the water cooling and the steep thermal gradient. And then that crucible is poured, the molten material is poured into ingots. So the pouring temperatures, AZS, alumina zirconia silica, is maybe 1800 to 1900 degrees C. Alumina is around 2000 degrees C. Alumina chrome is around 2300 degrees C. And magnesia chrome is about 2000 to 2300 degrees C. So all very high temperatures. So the rate of solidification is important because it's going to determine the final microstructure, the final grain size. So the rate of solidification is the cooling rate. It's going to be controlled by the thermal conductivity and the thickness of the mold material. So carbon graphite molds are the most common. They have good thermal stability. Carbon and graphite decomposes at very high temperatures. It has low thermal expansion, high thermal conductivity. So it has good thermal shock resistance. So from a thermodynamic viewpoint, it's stable at high temperatures because of the high thermal expansion and high thermal conductivity. It has good, because of the low thermal expansion and high thermal conductivity, it has good thermal shock resistance. So it's a good material to make the molds out of. So this is what a mold would look like. The inner lining here, this thin black line, that's the graphite. So there's graphite plates here forming the mold. And then there's an annealing powder that surrounds the graphite. That's your insulation. And then the final line here is a metal shell. So there's a metal shell, an insulating powder, and then the graphite mold material. So again, the rate of solidification is controlled by the thermal conductivity of the molds, and that controls the final microstructure. So a thin carbon or graphite mold, that gives rise to a slower cooling rate, and that produces larger crystal sizes. So when this graphite mold is real thin, um, heat is extracted very slowly because you have a lot more annealing powder. So there's more insulation. So that gives rise to a slower cooling rate. If you have a thick carbon mold, that high conductivity carbon makes a faster cooling rate and smaller crystal sizes. So as this graphite gets thicker, that's going to increase the cooling rate, and the faster it's cooled, the smaller the crystal size. So again, the solidification rate controls the final microstructure. This is a casting in a thin mold, which might be around 1 inch thick. Of the skin surface, this microstructure is the surface on the outer portion of the ingot, which is in contact with the carbon or graphite. And the core is the center of the casting. So the surface is going to cool a lot faster than the interior. So there's going to be a microstructure gradient. So you're going to have the smaller crystals on the surface and the large crystals in the center. So this is about 100 microns. So these look like they're a little bit smaller than 100 microns, and then these are fairly large, maybe several hundred microns. So small crystals near the surface and large crystals near the core. And that's a 1 inch thick mold. So that would be considered slow cooling. And then a mold that might be thicker, maybe 3 inches in thickness. That's going to cool faster. So again, it's a 100 micron marker. These are the smaller crystals relative to these. And then in the center, these are maybe about 200 microns in diameter. So again, smaller crystals near the surface, large crystals near the center. And the thicker the mold, the faster the cooling rate. So overall, in any location, the smaller the crystals. So when you cast these materials, you have to worry about shrinkage cavities, which are on the order of 15 to 25%. So the voids are quite large. So when you cool from the liquid state, the solid state is going to be denser. It's going to create these cooling voids. So there's different ways to cast these materials. This first one, number one, is a regular cast. So this is a large block. It's cast from the top, and the cooling voids end up near the top. So when you go to use this material, if it's lining a glass tank, the sidewalls of a glass tank, the bottom surface would be the one you would put in contact with the molten glass. So that would be the hot face. Where the voids are, that would be the cold face. You can also tilt the mold. Number two is a tilt cast. So if you tilt the mold, the voids are going to end up in this top corner here. So you're going to have your hot face region on the bottom again. That's in contact with the molten material. And then this top would be the cold face. This area, basically void free. This might be put where the glass contact line is, where the most corrosion takes place. And then the third choice here is void free. So you put a riser in the mold, and when you cast it, these shrinkage voids end up in the riser, and then you just cut that off, and then you end up with a solid refractory. So there's various ways to cast the material, but you have to be aware of where these voids are. So these fused cast refractories have pretty unique microstructures. They have large crystals. These crystals are interlocking and pretty much basically no porosity or very low porosity. So these types of fused cast refractories have some very unique properties, and compared to the sintered version, they're going to have very high hot strength. They're pure high temperature materials, very dense. They're going to have abrasion resistance, and their main property is high corrosion resistance. So these are high purity, dense materials uh, made primarily for their corrosion resistance. Unfortunately, the drawback is these have very poor thermal shock resistance. So if you're making fused cast refractories to line a glass tank, you put them in the furnace floor, maybe, and the sidewalls, perhaps even the roof, and you take it up to temperature very slowly, and you keep it there. So you avoid the thermal shock issues. So the AZS material, alumina zirconia silica, you're going to have polycrystalline alpha alumina about 42 to 50%, and then polycrystalline ZrO2, 31 to 40%. And then you're deliberately putting in the silica to form a glass. So you're going to form a very viscous glass, 15 to 21%. So you're going to have large interlocking crystals, and the long annealing time um, helps grow large crystals. And again, the long annealing time, you need that to remove the stresses. So you're going to end up with a very dense material, basically no porosity except for the shrinkage cavities, um, which you know where they're going to be located, so you can adjust for the application. Or if you put a riser, you can remove those shrinkage cavities. So this is what an AZS refractory microstructure looks like. This is 100x, and the micron marker is 200 microns. So at 100x, the field of view here is about 45% alumina, 33% ZrO2, 20% SiO2, and there's some Na2O contamination. So these bright white crystals are zirconia. This one, when you do the chemistry on this one, the EDS chemistry, it's about 98% zirconia, and the balance is hafnia. So all the white crystals, including these small white crystals, are zirconia. These small crystals are dispersed in alumina. So the small zirconia crystals are the eutectic microstructure. They're dispersed in alumina, and that alumina is basically 100%. So you have large zirconia crystals, small zirconia crystals in the eutectic microstructure and alumina matrix. And then this gray region is the silica-based glass. So that's about 60% silica, 30% alumina. Your Na2O is about 6%. There's some zirconia also dissolved. Lime, iron oxide, and TiO2 are some of the impurities. So you have zirconia crystals dispersed in a glassy matrix or an alumina matrix. So the zirconia is monoclinic zirconia. And then This is the eutectic microstructure where you have zirconia dispersed in alumina. So that's also monoclinic zirconia. And then your glassy phase, when you heat this refractory up, it softens. It's very viscous, but it softens. And then when the zirconia goes from the monoclinic to the tetragonal version and back and forth, it absorbs the transformation. So the glass is put in there deliberately to account for the phase change monoclinic to tetragonal zirconia and the volume changes. If the glass is too fluid at the use temperature, it'll exude from the refractory because the viscosity will be too low. There's actually an ASTM test to measure how much glass diffuses out of the refractory. If that's the case, too much glass diffusing out of it, that's also a source of contamination if you're melting in a glass tank. So if you map with EDS the aluminum, it's in blue here. The little black voids is where the monoclinic precipitate is. The purple is ZR. So you can see the large crystals and then the smaller crystals in the eutectic microstructure dispersed in the alumina. And then silicon is in the glassy matrix. So you can see the glass where it's located. So that's in green. So that's silicon in the glass. And the sodium, the contamination is also in green here. It's in the glass. It's same location as the silica. So AZS has this thermal expansion issue. We went over this when we talked about zirconia. So percent thermal expansion versus temperature. The solid line is the first heating and cooling cycle. So you start out with the low density monoclinic, normal thermal expansion until you hit the transformation temperature. In this case, it's 1179 degrees C. Volume decrease going to the high density tetragonal phase, and then normal thermal expansion. Then when you cool it back down, in this case 1040, it goes back to monoclinic. And then when all the transformation takes place, you have normal linear contraction and an offset due to microcrack formation. So the glassy phase in an AZS refractory cushions this tetragonal to monoclinic transformation. And when we talked about zirconia-based refractories, we were adding a stabilizer like CaO or Y203 to put it all in the cubic phase to make a useful refractory. But in an AZS refractory, we're staying with a high temperature material. So we're using the glass phase to cushion this. We're allowing the transformation from monoclinic to tetragonal to take place. Whereas when we talked about zirconia refractories, we're keeping it all in the cubic phase. So this thermal expansion issue, the irregular expansion of ZrO2 due to the transformation from monoclinic to tetragonal, that irregular expansion is accommodated by the cushioning effect of the silicate-based glass. You still have to go through controlled heating and cooling cycles. I mentioned these blocks could be used to line a glass tank, and that you want to really avoid heating and cooling cycles. You don't want to disrupt the microstructure of the refractory, so you heat it up very slowly, and you keep a glass tank at temperature for many years. And this glass exuding at high temperatures from the refractory can cause areas of high viscosity glass, known as cords or knots, and they're glass defects. So you have to um, kind of control the viscosity. You want it a high enough viscosity so it doesn't diffuse out of the refractory, but it has to be low enough viscosity to cushion the transformation. So in AZS refractory, because of the high zirconia content, it has excellent corrosion resistance. And as you increase the zirconia content, the corrosion resistance goes up. Because it's a hard material, it has excellent wear resistance. But a fully dense refractory like this, no porosity, uh, relatively high thermal expansion, the thermal shock resistance is extremely low. Uh, when we run thermal shock tests on AZS or any fused cast refractory in our lab, the normal test, thermal shock test, you cycle it multiple times, usually at least 5 times. Um, typically, a fused cast refractory might last one cycle. It's that really, that poor? So all of these have low thermal expansion, low thermal shock resistance. So there's two versions, an AZS low and an AZS high. These are the bulk densities, um, 3.5, a little higher DrO2 content. It goes up to maybe 3.6, 3.7 grams per cubic centimeter. So the low version is about 32 to 36% ZrO2, and the high version is a little bit higher zirconia content, 39 to 41. Porosity is less than 1%. So low porosity, dense materials, going to have high strength. So the crushing strength, um, 29 to about 75,000 PSI. So they're very strong. They're high temperature materials, so the refractoriness under load is greater than 1700 degrees C. The thermal expansion at 1000 degrees C and percent, 0.6 to about 0.8, 0.6 to maybe 0.9. So they're not extremely low expanding materials. So I mentioned the ZrO2 contents. The balance is silica and alumina. Silica will drop and alumina will drop a little bit in the higher zirconia version. And impurities might be Na2O, Fe2O3, and TiO2. So these are the same chemistries I just showed. So the phases present in both cases are going to be alpha alumina, monoclinic zirconia, because we're at room temperature. As you heat it up, it's going to transform the tetragonal around 1100 C, and then the balance is the glassy phase. So the high zirconia version has a little bit more monoclinic zirconia, a little bit less alumina, and a little bit less glass. So this small difference in ZrO2 content really changes the corrosion resistance. So the corrosion resistance in the high AZS version is about 20% better than the low AZS version. And the glass viscosity, it's more viscous in the high zirconia version compared to the low zirconia version. As you go up in zirconia content, the cost of the refractory goes up also. But you have better corrosion resistance and less contamination from the glassy matrix. Alpha alumina is polycrystalline alpha alumina, 95%. Because of the sodium impurity, you're going to have some beta alumina, maybe 5 to 10%. There should be no glass in this material. assuming the impurities are low. So any glass is going to be less than 1%. So it's primarily alpha alumina with some beta alumina. And again, beta alumina is Na2O11Al2O3. Large crystals, they're going to interlock. Crystals grow also during the annealing process. They're dense, no porosity, but we always have the shrinkage cavity. The beta alumina is basically 99 to 100% beta alumina, less than 1% glass. So it's all Na2O, Na2O, 11Al2O3. It's that phase. Again, large crystals, dense, no porosity. And then there's also another version, roughly 50% alpha alumina and roughly 50% beta alumina. Maybe a little more glass here, but less than 2%. So this one is a combination of alpha and beta alumina. And you're adding Na2O to adjust this composition. Again, these are going to be large crystals. They interlock, provide high temperature strength, and they're very dense materials, very little porosity. So this is a microstructure of a beta alumina. The black is the porosity. This is actually the edge of the refractory. So this is not porosity. It's just the resin matrix that's used to make the polish section. This is 20X, and that's a 1,000 micron marker. So this one is about 92% alumina, 6% Na2O, and you have some silicon and lime present. That's going to give rise to the glassy phase. So you can see these long needle-shaped crystals, rather long, and they're interlocked. If you do the mapping for aluminum in blue here, it's a rather uniform distribution of alumina. And since it's beta alumina, if you map the sodium in green, it's a uniform distribution. So it's a beta alumina. And if you also map the oxygen, it's very uniformly distributed in red here. So chemistry is very uniform in those materials. Alpha alumina has really good corrosion resistance. It's hard material, so it has excellent wear resistance. And for all of these, because they're dense, they're going to have very poor thermal shock resistance. The beta alumina is excellent in contact with a molten material that contains an alkali. So this beta alumina will decompose to alpha alumina and Na2O if no alkali is present. So if you're melting a glass that has an alkali in it, this is a good choice, the beta alumina. If there's no alkali present in the glass, it'll diffuse out of the refractory, and that'll cause issues with cracking in the beta alumina refractory. So this one works well with, let's say, glasses that have an alkali present. Good wear resistance, but again, very poor thermal shock resistance. The combination of alpha and beta alumina has good corrosion resistance. Again, there has to be an alkali present because of the beta alumina. Wear resistance is excellent, and then again, thermal shock is very poor. So here's an alpha alumina, a beta alumina, and an alpha beta alumina. These are the densities in grams per cubic centimeter, roughly 3.8. This is high alumina, so it's higher than the beta alumina, which is around 3. And then the alpha beta alumina is in between, maybe 3.4. The porosities on these are pretty low, less than 5%. This one's less than 2%. Dense materials are going to have high high strength, so the compressive strength is from, this is from 21 to 36,000. This is about 3,000 to 10,000, and this one is about 21 to 36 also. They're high temperature materials, so the RUL, refractoriness under load, is greater than 1750 degrees C, and the thermal expansion is relatively high. This is percent at 1,000 degrees C again. So about 0.8, 0.7, and 0.7. So the alpha alumina is about 99% alumina. The beta alumina is about 94% alumina. And then the alpha beta alumina is in between, around 95, 96% alumina. The main impurity here is Na2O. 5 or 6% has to be there to make beta alumina. So you have a combination of alpha and beta alumina, maybe 3 or 4%. So basically, these are alumina, and then you have the Na2O in the beta alumina and the alpha beta alumina. MgO, CaO, Fe2O3, and TiO2, SiO2 are the impurities. So the same three materials, the same three chemistries here. So alpha alumina is 95% alpha alumina because of the trace amount of Na2O. You may have 5 to 10% beta alumina. And because it's relatively pure, low SiO2, you're only going to have less than 1% glass. The beta alumina is going to be close to 100% beta alumina, small amount of glass because of the silica again. And then the combination of alpha and beta alumina, roughly half alpha alumina, half beta alumina. And this one has a little more silica, so maybe 2% of a glass. The alumina chrome is polycrystalline Al2O3, Cr2O3. It's a complete solid solution. So maybe 50 to 70%. And you can have a complex spinel, RO, R2O3, maybe 40 to 55%, depending on the impurity level. So large interlocking crystals, again, very dense, no porosity. Because of the high chrome content, the corrosion resistance is really good, especially in contact with the molten glass. But again, the Cr2O3 discolors the glass as it corrodes. Hard material, excellent wear resistance, but again, low thermal shock. So the alumina chrome, maybe 3.8 for the density grams per cubic centimeter. These materials on this data sheet, maybe 3 to 6% porosity, over 20,000 psi for the cold crushing. And the RUL is also very good, greater than 1750 degrees C. The thermal expansion is relatively high, 0.8% at 1,000 degrees C. So you have Al2O3, close to 60%, Cr2O3 in the high 20s, 26 to 28%. And then because you have materials like MgO and CaO, you have that complex spinel forming. Silica, MgO, CaO, Fe2O3, and TiO2 are typical impurities in the chrome ore. So same chemical composition. So you have the chrome alumina solid solution, maybe 50 to 70%. Then your complex spinels, because of materials like MgO, forms an MgO Cr2O3 spinel, maybe 40 to 55%. And you have your silica, your iron oxide, you're going to form some glass. You can also have an MgO Fe2O3 spinel. So that's in the complex spinels. And then the last one here, MgO-CR203, is going to be polycrystalline MgO, maybe 40 to 45%. And then you're going to have some complex spinels. These are the RO, R203 materials. That may be 50 to 55%, and a small amount of glass from the impurities. Again, all of these are large interlocking crystals, dense, very low porosity. So the corrosion resistance is really good, especially this is a basic refractory because of the high MgO content. Cr203 is a neutral material, but MgO is basic. So it has excellent corrosion resistance in contact with the molten metal and also basic slags. Excellent wear resistance, it's a hard material, and very poor thermal shock behavior. So these are, depending on the chemistry, 3 to 3.4 grams per cubic centimeter. These particular ones have a higher porosity, 10 to 15%. And that gives rise to a lower cold crushing strength, less than 15,000 PSI. Has very good RUL or refractoriness under load greater than 1700 degrees C. Because of the high MgO content, the thermal expansion is now over 1% at 1000 degrees C. So this has about 55% MgO, 20% CaO. There's some alumina, 8 to 15%. Fe2O3 is the other major component, 8 to 11%. Small amounts of TiO2, CaO, and SiO2. So the typical impurities in the chrome ore. So looking at the chemistries here, the phases that result, periclase is MgO, 40 to 45%. A complex spinel could be an MgO Fe2O3 or MgO Cr2O3 or MgO Al2O3, 50 to 55%, and then a small amount of glass because of the silica present, usually less than 3%. So that finishes up what I have on basic refractories. Next class, I want to go over the non-oxide refractories, which are carbon, silicon carbide, and silicon nitride. And once we finish that, that'll give us the background we need on the different chemistry, different refractory chemistries. So next week, we'll spend 2 lectures on the composite materials, which are pretty much carbon matrix composites. So next class, we'll go over carbon, silicon carbide, and silicon nitride. The following week, we'll go over the carbon matrix composites. It'll take at least 2 lectures on that. So have a good rest of your day, and thanks for listening in again.
Thank you.
Thanks.